Colorful spin tops have fascinated all of us in our childhood days. A top spinning fast stays upright for a considerably long time, balanced on a very small, sharp tip. No way can we ever get a stationary top stay upright like that. This suggests that a rotating top acquires some property which helps the top to stay upright. Let us talk about this property called angular momentum. Usually, when we think of rotation, we think of a solid object rotating about a fixed axis. For example, a merry-go-round, propeller of a helicopter, etc. However, we need to broaden our concept of rotation. This car is moving on a straight road with linear momentum p. It is therefore in linear motion. Let us observe the same motion with respect to an observer standing at any point O called the origin. With respect to this point O, the position vector of the car is r. We can see that although the car moves in a straight line, its position vector r rotates around O. So, we can say that the car undergoes angular displacement with respect to O. Thus, the same car can be attributed rotation with respect to the observer at O. We can therefore conclude that any moving object can be attributed rotation with respect to some fixed point or axis. The object is then said to possess angular momentum about that fixed point. The car therefore has angular momentum with respect to the observer. But what is angular momentum? Angular momentum for a single particle is defined as the moment of linear momentum. It is a vector quantity whose symbol is L. According to this definition, at position A, the angular momentum of the car about O is given by vector L is equal to vector R cross vector P. To find the direction of the angular momentum, vector L, we slide vector P until its tail is at O. Then we use the right-hand rule for vector cross products, sweeping the fingers from vector R to vector P. The outstretched thumb then shows the direction of angular momentum. The direction of the angular momentum vector is always perpendicular to the plane formed by the position vector R and linear momentum vector P. The magnitude of angular momentum is PR sine theta, where theta is the smaller angle between vector R and vector P when these two vectors are tail to tail. It is equal to PR perpendicular or RP perpendicular. Here, R perpendicular is the component of vector R perpendicular to vector P, and P perpendicular is the component of vector P perpendicular to vector R. The SI unit of angular momentum is kilogram meter square per second. Clearly, for the observer standing at O, the car always has some finite angular momentum. Does the angular momentum depend upon the choice of origin? Let us find out by viewing the same motion with respect to another observer standing at O'. We can see that the angle between vector R and vector P is always 0. So, sine theta is always 0. As a result, the angular momentum of the car with respect to this observer is always 0. Thus, the angular momentum of the same car with respect to two observers standing at different points is different. Since the angular momentum depends upon the choice of reference point, it is not an intrinsic property of the object, unlike linear momentum. Also, it can be shown that the rate of change of angular momentum of a particle is equal to the external torque acting on it. It is very clear that if tau is equal to 0, dl by dt is equal to 0, which implies that L is constant. This law holds for many particle systems as well. A spinning top also possesses angular momentum about the line AB, whose direction is given by the right-hand rule. If we neglect friction, we can say that there is no external torque acting on the top. Thus, there is no change in its angular momentum. Therefore, its angular momentum is conserved. It means that neither the direction nor the magnitude of angular momentum changes. Hence, it keeps spinning in an upright position. In reality, under the action of external torques arising due to friction and gravity, the top gradually slows down and falls. Summary: any moving object can be attributed rotation with respect to some fixed point or axis. The object is then said to possess angular momentum about that fixed point. For a single moving particle, angular momentum is defined as vector L is equal to vector r cross vector p. It is a vector quantity. Since angular momentum depends upon the choice of reference point, it is not an intrinsic property of the object. The rate of change of angular momentum of a particle is equal to the external torque acting on it.